So, hi everyone again. I guess we're live already. So,
Yeah.
so this is a third paper of this session. So the paper is using machine learning to build test oracles, an industrial case study on elevators dispatching algorithms. So this is a work from Heitor and colleagues, and it also presents a really nice industrial case study. Heitor, you have 30 minutes for a presentation, so please try to leave us something around 5 to 10 minutes for the questions, okay?
Okay, thank you. Okay, so thank you. My name is Aitor Arreta. I am a lecturer and a researcher at the University of Mondragon. And I'm going to present this paper, which was done in collaboration with my colleagues Jon Ayerdi, Miren Illarramendi, Aitor Aguirre, Goiuria Sagardui, and Maite Arratibe from 3 different centers, Mondragon University, Ikerlan, and Orona, who is the use case provider in this case. So let me explain first what a cyber-physical system is. Cyber-physical systems are complex systems integrating cyber-digital technologies with physical process. Their software is highly complex, as they usually implement most of the functionalities of the CPS, some of which might be safety critical. And as in any other kind of software domain, the maintenance of this software is extensive to add new functional and non-functional requirements, to correct bugs that appear in production due to legislative changes, or because the hardware gets obsoleted and the system also degrades. So our case study comes from the vertical domain. It's an elevator, and it's provided by Orona, which is one of the largest elevators company in Europe. So our system under test inside this system of elevators is the traffic master, which is the processor in charge of assigning an elevator to each call from the passengers. This is communicated to the lift controller through CAN, whose goal is to control the dynamics of each elevator. And it also communicates through CAN with user interfaces. Lastly, in the most advanced elevators, it is also possible to communicate through an Ethernet with the access control system, which allows for limiting the floors that each passenger can travel to. Orona has a well-established process for the maintenance, verification, and validation of their system, and it has a total of 10 steps, which can be divided into 3 main steps: the software in the loop phase, the hardware in the loop phase, and operation. Usually, when a new release is being done, it usually takes around 1 year to ship, which is a high time if we compare this with other software industries such as web engineering. However, in occasions, this has to be the release has to be shipped fastly. And this was, for instance, the COVID-19 situations that they had, where they had to change the software to limit the attendance of each elevator to a maximum of 2 passengers per elevator. They also had to minimize the queue in a floor, and still they had to keep a good overall quality of service performance of the system of elevators. So in this case, testing is done through simulation. In the first step, we have a software in the loop, where simulation, where both the software and the physical layer of the cyber-physical system is simulated through a domain-specific simulation tool named Elevate. Here, a set of passengers. Sorry, I'm going to put the laser. A set of passengers traveling from a floor to another is simulated, and the simulation returns a set of quality of service metrics, such as the average waiting time. So, for instance, the average waiting time is the average time that the system of elevators needs to that each passenger has to wait until it gets attended by the elevator. And in this case, the average waiting time is highly employed in this domain to test the software, because the studies have shown that passengers' perception on the correct functioning of the elevator depends on the time they are waiting an elevator to arrive, rather than the time they spend to travel inside an elevator. And in a second phase, we have the hardware in the loop phase, where in this case, the software is embedded into the real-time targets with all the real-time infrastructure, including real-time operating system, the drivers, and so on. And the physical layer is emulated into a real-time hardware high performance test bench. Sorry. Okay. So to allow full test automation, test oracles are required. Within the current process, Ororina uses regression test oracles. So to this end, first, a stable version of the algorithm is used to obtain reference values for certain test inputs. And a test input in this context refers to a passenger file, which indicates passengers traveling from a floor to another floor in a building over time, and the building information, which provides information in relation to the building. So, for instance, here we have a building of 8 different floors with 3 different elevators, and each elevator will have certain dynamics and so on. As an outcome, we have a set of test results, which are the quality of service data. This is average waiting time, or average time to destination over time. So after this, it is executed. A test is executed with the current version of the dispatching algorithm. It is again obtained the test results, and the quality of service data over time is compared against the reference signal. So in these validations, real and theoretical traffic profiles are used. The good point of theoretical traffic profiles that are, here is an example, is that we can generate them for any kind of elevator installation, and many of them. But also the good point of real profiles is that they are more realistic, but it requires to install some monitors on the installation. Here is, for instance, another example. Here we can see the differences, right? For the traffic data of a building of offices. So early in the morning, we can see that there are a high number of incoming calls and a few number of outcoming calls. Later, from 1 to 3 o'clock, we see here an increase in the outcoming calls. This is because people are going home to have lunch. Later here starts increasing, and later in the afternoon we have an increase in the number of calls for the outgoing calls. As can be seen, the difference here, the number of interfloor calls. This is that floors that are calls that are between floors in the system of elevators is larger in the theoretical traffic profiles. So the key problems of using a regression test oracle in this context is that a test needs to be executed multiple times under different software versions. And this, the test execution time at software in the loop takes from minutes to hours. And in the hardware in the loop, where we have a real time, where the simulation is in real time, the tests take from hours to 2 days. offline testing is required here. So if we have a bug early in the simulation, we are not aware of this. It is also not possible to use the test oracle at operation, because in operation we don't have a reference value, and also it is not possible to test some functionalities such as the human-machine interfaces, because essentially clicking at the same time it's basically impossible. So in this paper we propose DARIO, the dispatching algorithm oracle, which relies on machine learning algorithm, and it has two different phases. The training phase, where we feed a machine learning regression algorithm with labeled data of passenger traffic data with average waiting time data. We have used in this paper only average waiting time and no other quality of service measure. This should be for test executions that labeled as pass, that they consider they are correct. And the goal of the algorithm is to learn which average waiting time should be for certain passenger data features. The result of this phase is a machine learning model. And later there is the test phase, the testing phase, where the test is executed at any level, given some inputs. Some test data extraction is processed in order to provide the passenger traffic data to the predictor, which infers which should be for this data the average waiting time that it should have, and it is compared against the average waiting time that the system has provided. And this returns an overall verdict, a pass or fail, and a quantitative verdict over time. So we talked with domain experts to see which type of failing patterns they were considering, and we extracted 3 of them. One could be a failure due to a high peak. This is if we have here the reference value and we suddenly see here a peak. This could be provoked by a bug. It could be also a failure due to a high time out of bounds. So for instance, in this time window, we have a high time out of bounds, and this can indicate that there is a bug that was exhibited in this time. Or we could have also due to a constant degradation. So we formalize this by having a numerical verdict over time, where a positive value indicates that the system was behaving as expected, and a negative one that the expected value was above the expected one. And the numerical verdict was compared against 3 defined thresholds, one per failing pattern, and these thresholds had to follow the following constraints. So to evaluate this approach, we aim at answering 2 research questions. The first one was which regression learning algorithm yields the most accurate test verdicts when trained with theoretical passenger data. And the second one is similar, but instead of using theoretical data to train, we train them with real passenger data. As case study, we used Orona's CGC algorithm, which is the most widely used algorithm, not only in the context of Orona, but in the context of most system of elevators. We used this because they have many versions of it. They implement for important buildings like this one, a specific functionality and so on. The complexity is quite high because it's continuously evolving. And also the good point for the evaluation is that it is a deterministic algorithm. So this is the evaluation. And we tested this in the building from Telefónica's headquarters, which is Telefónica is the the largest telecommunication companies in Spain. And it had a total of 10 floors, 6 elevators, each one carrying a maximum weight of 1,250 kilograms, and 16 passengers. Why we used this? Because we had data from real passengers in that building. So as evaluation metrics, we used mutation testing to seed faults. In total, we generated 99 mutants, but 18 of them were leading to crash. And these kind of faults can be easily detected without any oracle. So in the end, we used 81 mutants. The baseline that we used was the regression oracle. This is a previous version of the system under test, used to obtain the real average waiting times. And as metric, we use the precision, recall, F1, and accuracy. We selected a total of 5 regression learning algorithms, these 5 that were quite fast on training. It took some seconds only. And we generated 4 different scenarios. In the first and second scenario, for answering the first research question, the training was done with theoretical passengers data, and the testing was done in the first case with theoretical profiles, and in the second case with real profiles. And scenarios 3 and 4 aimed at answering the second research questions, and they were trained with real passenger profiles and tested with real and theoretical passenger profiles. So the results for these scenarios are this. We can see that in the first and second scenarios, the supervector machine and the regression theory algorithms yield the highest values when compared to the rest ones. And in scenario 3, the values of the supervector machine, especially for accuracy, were quite low. But however, the regression tree was quite competitive, despite the rest of the algorithms not being that competitive. But however, in scenario 4, the results of the regression tree also were not very good. So to answer the first research question, supervector machine and regression tree algorithms performed best. However, their performance slightly decreased when trained with these profiles, but tested with real profiles. And in the case of the second research question, the regression tree performed best in the third scenario, but the performance of all the algorithms were quite bad when tested with theoretical ones. So from the evaluation, we extracted the following 3 lessons learned. The first one was that training is convenient to be done with the same type of testing. So if we are going to test with real theoretical profiles, use the real theoretical profiles for training the algorithms. And if using theoretical ones, then train with theoretical ones. However, real passengers data is important if we want to push these test oracles into operation and not limit the validation only for the software in the loop and hardware in the loop phase. And this is important because, for instance, in the case of the development of the COVID-19 functionalities into the dispatching algorithm, we could not thoroughly test these versions of the software. So it is also appropriate to test it once that they are in operation. And this can also allow activities like DevOps in the context of cyber physical systems. However, also the use of machine learning algorithms as test oracles increases the uncertainty in relation to the test verdict. And this issue was raised by having our conversation with Orona's engineers, that they said, okay, we have a verdict, but we are unsure about its correctness, right? So, as conclusion, we have proposed in this case DARIO, a test oracle that relies on machine learning to test elevators dispatching algorithms. This kind of algorithm provides a reduction in time compared to traditional regression oracles because training takes only a few seconds, but testing takes minutes to hours at software in the loop and hours to days at hardware in the loop. It permits new testing activities such as testing up operation time and also testing at hardware in the loop with real human-machine interfaces. But however, we have this limitation of having uncertainty in relation to test verdicts. In the future work, we would like to work on handling better this kind of uncertainties. First, uncertainty in relation to the machine learning models. This is to see whether the results provided by the machine learning algorithms are quite correct or not, or they have probability of being wrong. But also uncertainty of the system itself. And this is especially interesting for operation because we don't know which are the weights of the passengers. In some cases, in some installations where you have to select which is the floor that you are going to, and the elevator directly assigns you the floor, there are ghost passengers, what means that they haven't pushed this button. So suddenly the elevator has more weight, or the wrong usage of the system, and so on. So thank you very much for your attention. And now, if you have any question, I will be happy to answer them.
Okay, so thank you very much, Ito, for the really nice presentation. So far, I don't have any questions in the chat. So let me start with a couple of them until the audience starting sending the questions. So I was curious about the scenarios that you mentioned. So you explored the 4 different scenarios, right? And the difference between them is basically what kind of data you are using for training and then for testing. Mm-hmm. So the scenarios 1, 2, and 3, they make sense to me. So in particular, the 2 and 3, because you're trying to predict the data in the real use case. But I was a bit confused about the scenario 4, so I would just wanted to ask you if there is any scenario that you have in mind for what it would be interesting or important to train on the real data from the elevators and then to apply the test on the theoretical data. Is this useful?
Yeah. Yeah, you are right. This is we just wanted to know whether the only point that we could see this maybe useful was that perhaps in when you training solely with real training data, we could have some patterns that were not in theoretical, right? And the point with the theoretical is that we can have a large amount of these data of these tests, and if we don't have available a model with these data, with these tests, and only we have available with real training data, then we can somehow use a large amount of theoretical tests for this. But this is the only case. Another case could be if we have many kind of installations, and we are able to train the models in these installations with data from those installations, and later we want to have different tests of different installations. But it is true that it is the case with less probability of having use, of having a practical implication.
Even in the cases that you mentioned, I guess you mentioned that if you have a real installation, you can use that data to make the predictions. But again, I was not able to think about a scenario where predicting the theoretical values would be like interesting. But maybe that could be useful for something related to the simulator.
Another case is that, for instance, in the software in the loop case, the fidelity of the simulator is the lowest one, and in the hardware in the loop, the fidelity is the highest one. So if you have data from real installations, then you can train this model and use it at the hardware in the loop test without using it without having any execution of theoretical tests in this case, where executing tests in the hardware in the loop test bench takes hours. So this can be, it's a bit tricky to have this scenario, but yeah.
Mm-hmm. Okay, so we have a question from Alejandra. So she congratulates you for the nice work, and then she asks if the accuracy reached it's enough for the company that you are working with, or if you're still planning to work on improving accuracy.
Yeah, this is a very good question, and it's what they are wondering if if they are going to have a bug without being noticed or not. I think that for the case of the COVID software development phase, it could have been enough, because it was a really fast case, right? But for the case of the software that is being shipped yearly, I think that they would invest more in using the regression test oracle, and they would ask us to improve this accuracy. So this is now the situation that we are trying to work on improving the accuracy, and in case of not being possible to improve it, at least say be careful, because in this case the uncertainty of the model was too high. So maybe it is appropriate to execute the test from second 50 to second 5,000, or for the time where that happened, right?
Okay, thank you. So on top of Alejandra's question, so that she's talking about accuracy, so I noticed that you mentioned at some point that you used the accuracy because it was the only metric that was able to capture the true negatives, and that's important to your problem. So I understood that you have these two different classes, right? So you have the...
Yeah, so let me include this. So so in this case, the false negative is when the test oracle returns a pass and the regression test oracles return a fail. So this is important, but it was also important when having false positive. So this is that the DARIO returns a fail and the regression test oracle returns a pass. So then the problem here is not I want to catch as many bugs as possible, but classifying them well. So in this case, for instance, the mutation score that we achieved wasn't high. It was around 20%. But what we wanted to do is that these 20% were classified well, and the 80% also, these ones were not considered bugs. They will be bugs if bugs for the kind of tests that we are doing. But later we have other kind of oracles that they are aiming at cataloging these mutants as bugs. So really the mutation score wasn't important in this case, because it is more related to what tests are being executed.
15 seconds.
Yeah. Okay.
To complete. So, but then, so for the attendees, they can move to the discussion room and continue the discussion with you. Okay. Okay. So thank you very much again, Nato, for your presentation.
Okay. Thank you.
Okay.
See you.